Well, I think we're ready to get started with the 2012 Aquarium Lecture Series. I'm very, very excited. As you probably realize, I'm not Sunny, who usually does this. She has gone on to some amazing adventures, so I've actually been lucky enough to take over for her in arranging these great programming and other events that go along with the lectures. So of course, we'll do the regular spiel that some of you are probably used to before our lectures that we always have. But of course, Lowell Institute allows the aquarium to do these for free, so we're very appreciative of those. My name is Gina Cerrito, and I will be coordinating these programs. If you haven't already joined our mailing list, I ask you to, because we enjoy sending you about all the exciting things that we have going on. So there's brochures outside, and we do have a registration list as well. So we like to have as many people on that list as possible, and do share it with your friends when we send it out. So if everyone at this time could silence your cell phones as well, I'm sure our speaker would appreciate that as well. And as always, we do try to make the lecture series heavy on knowledge and light on the earth, so we offer recycling and composting as part of our refreshment service. So those plastic cups are actually not plastic, they're made out of corn, so those can actually be composted, and we have lots of different colored bins outside. As well. So our next lecture is actually coming up next Thursday, and we're very excited because it's our own aquarium staff that will actually be speaking. Paul, Leonard, and Joanna Razi will be here. They've just returned from an amazing trip in South Africa and did a lot of penguin research, so they're very excited to share that with our aquarium public as well. And now on to our exciting lecture for tonight. Dr. Stephen Pekar is a geologist with interests that encompass a wide variety of problems related to the oceanographic and climate evolution of the late Cretaceous and Cenozoic periods. To tackle these problems, he has collected various types of core samples from estuaries to the deep sea. These are used to extract information pertaining to climate, ocean, and global sea level signals as far back as 1 million years ago. Dr. Pekar has earned both his master's and his Ph.D. in geology at Rutgers University, and he is currently an associate professor at Queens College in Flushing, New York, and an adjunct associate research scientist at Columbia University's Lamont Doherty Earth Observatory. Lots of stuff in there. Tonight, Dr. Pekar will share his recent project that is using sedimentary cores from Antarctica. These cores were discovered recently during the Integrated Ocean Drilling Program, which some of you probably picked up some interesting CDs that you can look at afterwards about the program. They are extremely rare and are able to show us what the Earth with elevated CO2 levels looked like 25 million years ago. So in essence, these cores will allow us to see our future planet Earth by looking back at our past. So please help me welcome Dr. Pekar.
Well, thank you, Gina. I just want to thank her for inviting me all the way up to Boston. I'm from New York City, as you can probably tell from the accent. And also, I've met many of the staff of this really great aquarium. I really enjoyed exploring it today. You've got a great facility here, and so it was really great to see for the first time. I've always gone up to Boston to see other things, so first time. So anyway, so today's talk, I'm going to be talking about past climate changes and past ice volume changes, mainly in Antarctica, and summarize some of the methods for estimating ice volume. In this case, we're talking about Antarctica because up until about 3 million years ago, we only had like a unipolar world. Okay, only Antarctica was frozen over. We didn't have the Greenland ice sheet, and the northern hemisphere was basically ice-free. And there's two methods to do that. We can actually, one way, you can almost imagine, on a continental shelf, sea level goes up and down. And if you can take some cores, you could look at the sediments and the fossils and figure out how water depth went up and down, right? It's a little bit more complicated than that, and I'll show you that in a few moments. And the other one is actually using geochemistry from cores taken from the deep ocean. And you're probably going, wait. We're going to get ice volume from little fossils from the bottom of the ocean. Okay, so you got a bridge you want to sell me too. Okay, right. I will show you how that's done also. And then start giving you some estimates of how big the Antarctic ice sheet was during times of elevated CO2. Today, carbon dioxide in the atmosphere is around 390. Okay? We're projecting, the climate scientists are projecting that CO2 will be as high between 550 up to maybe up to 1,000 parts per million. We haven't seen that in a long time. And then finally, talk about some of the results from the ocean drilling program. So the history of the ocean drilling program goes back over 40 years. It started actually in the 1960s. It was called the Deep Sea Drilling Project. And this was actually there to basically try to prove plate tectonics. Now, for most of you youngsters out there, you go, wait, plate tectonics, hasn't that always been around? No. In the 60s, it was still quite controversial. And before the 60s, it was heretical, okay? People, it was really controversial. And so anyway, so the Deep Sea Drilling Project, using Glomar Challenger, big drilling ship here, we were able to take cores from the bottom of the ocean. And in fact, so it would extend a drilling pipe through thousands of meters, maybe 10, 15,000 feet of water, and then drill into the sediments, recovering many hundreds, maybe 1,000 feet of sediments at a time, going back tens of millions of years in some cases. Now, the next iteration began in the 1980s. It was called the Ocean Drilling Program. It used the largest ship, prettiest ship in my eyes also, and it included many different countries, and it was able to drill up to 2 kilometers below the sea floor. Okay, 2 kilometers below the sea floor, and recovering records back to about 165 million years ago. 165 million years ago, it was basically Jurassic Park, to give you an idea of what the Earth was like. And so this is a map showing what the Deep Sea Drilling Project, where we drilled during that project from the late 60s until the early 80s. And you can see the numbers just represent the site number. You can see that there's a lot of sites that we drilled. And when we add the ocean drilling program, it starts looking like, whoa, maybe we don't have to drill them anymore. We have a lot of sites in here. However, if you take a look at other places along in the ocean, like in the Southern Ocean here, very few cores, in the Arctic Ocean, almost nothing. And you can't see it on the map, but along the shallow sections here, shallow shelf, we can't get the ship in. We just can't drill in shallower waters. What shallower waters means, less than, say, about 300 feet of water depth. We just can't get the ship in. It becomes dangerous for the drilling. And so there's still lots of places that we really have big empty holes of our knowledge of understanding past climate and past oceanographic changes. And so the latest iteration is called the Integrated Ocean Drilling Program, IODP. And what this allows us, and what they did, is that we kept the JODI's resolution, so we can drill in the deep sea. However, to get down to deeper sections, we have a larger ship called the Chikyu, which is, I call the Godzilla ship, because it's much larger, and it can drill much deeper into sections where we can start exploring tectonics. Actually, it was the Japanese who built it, because we have to try to get a better handle and better understanding about subduction zones and active plate margins, for example, what happened in Japan just last year. Okay, perfect example. And so we have this ship, so we can drill much deeper. But then we also have something called mission-specific platforms. And that's what is a mission-specific platform? It's a platform that's mission-specific, which means it allows us, so some of the platforms can go drill in shallow waters. Other platforms can go into ice-infested waters, like icebreakers, and drill there. So now we can go into the Antarctic waters, we can go into the Arctic Ocean, we can get into shallow seas. We actually did a drilling project on an ancient coral reef in very shallow waters in Tahiti. Now that's a nice project to work on, let me tell you. I go to places that are very cool, actually cold Antarctica. I'll tell you about that a little later. And so there's 4 major science themes. Of course, the first one is the ocean, is climate and oceanographic changes. That's what I work on. That's what I'm going to focus in today. The other one is the biospheres. In fact, there's a new frontier of realizing that there's life just not in the upper centimeters and inches of the bottom, but going back tens of meters, maybe hundreds of meters below the sea floor, there's life. Okay, It's incredible. It's a brand new frontier. It's like going to another planet, a whole new biology, so on and so forth. And then we have Earth Connections, which is basically looking at fluids and looking at rock interactions. So like, for example, mid-ocean ridges, okay, where we have volcanism under the water. We have hot fluids moving through. These are some of the connections. And then finally, Earth in motion. With just have to say the Japanese earthquake and why it's so relevant to try to figure out more of this. And so, as a matter of fact, before I go any further, okay, so I'm doing this to a university crowd, and I can see the students, I can see the professors, and so here I am with the general public. How many of you are either like high school or college age, or know somebody of that age who likes science? Raise your hand. Okay, so the ocean drilling program, actually the IODP, Integrated Ocean Drilling Program, almost any aspect of science that you're interested in. If you like biology, Biosphere Frontiers, okay? This is the closest you're going to get to being Mr. Spock on the Enterprise and discovering new life forms, okay? If you like climate and oceanographic, Jacques Cousteau or the weatherman, of course, paleoceanography, okay? Earth Connections, you like hydrology, you like water fluids, Earth Connections, and of course if you into volcanism and so on and so forth, we have every type of the geologies and sciences. We have expeditions for. We actually put down remote sensors on the sea bottom to explore life and hot fluids, coming out of the rift systems. And so this is a great opportunity. And in fact, the United States is really great in this. They actually bring on 2 graduate students. We have 8 scientific slots on each expedition. And up to 2 of them could be just for graduate students. I wish I had that opportunity when I was doing my Ph.D. And so we actually had 2 graduate students going down to Antarctica on this drilling ship. What an opportunity. So, but let me start focusing in on the JOIDES Resolution, which is the drilling ship that we use. Oh, we lost all the colors? That's not good. We'll see. Okay. So anyway, it's a big ship. Yeah, it's losing a little bit of color tonight. Oh well, shucks. And it was such a beautiful ship too. But anyway, so it's a long ship. It's over 400. It's almost 500 feet long. It's about 10 school buses long, in fact. And with the drilling derrick, it gets up to over 200 feet, which is like a 20-story skyscraper, in fact. And so we think, of course it's a drill ship, first of all, but it's also a floating science research center. It's got about 30 scientists. It has about 100 support people, everything from the crew moving the ship, as well as the technicians doing the drilling, for example. And then, of course, we have cooks and everything that you need. What are the great things about being on the ship? The laundry's done for you, the cooking's done for you, the beds are done for you. Oh my, I haven't had this since I was 7 years old. But it's also a floating science research center. And this is, for me, this is the closest I'm ever going to get to being on, like in Star Trek, with the USS Enterprise. Because in this case, instead of boldly going where no one has gone before, in this case, we're boldly going where no drilling bit has gone before. And we're after cores, okay? Whether it's igneous rocks or sedimentary rocks. And so we're basically looking at the rocks, the sediments, the fossils, the chemistry of the rocks, chemistry of the sediments, to try to figure out what the past was like in terms of the ocean, in terms of the climate. And we have different scientists, everything from the paleontologists looking at the fossils, people who look at the sediments, we have chemists, we have people who use remote sensing, okay? Basically bombarded with the different instruments to try to figure out clues about the past. And in fact, this is really, like I said, this is the closest you're going to get to Star Trek. Because we have 30 scientists, we have 2 shifts, 2 12-hour shifts, so it's 15 scientists, duplicated. And on this ship, all the data that you collect on the ship is shared. Okay? So it's almost like kind of like an opposite of a reality TV show, okay? Where like here, like a reality TV, you're trying to compete and, here we're sharing, okay? The other one is, in reality TV, trying to win or beat somebody, here we're cooperating, okay? What a different world. This is what we want to live in, okay? As opposed to, having mud slung at each other and being voted off islands. And this is what we have. We are out there for 8 to 9 weeks sometimes. Our expedition was a little longer because it was all the way down near Antarctica. And, but it was 9 weeks. And to tell you the truth, we all missed our loved ones. We missed our favorite, bed or whatever, the little things, the creature comforts. But we all walked off the ship a little sad that the greatest adventure we ever had was over. And so the other thing I want to mention is just a few things about how successful the ocean drilling program is. It's been, first of all, it's the most successful, largest international scientific effort humanity has ever seen. Okay, we have over 20 countries involved in this. Okay, it's really like the Federation of Star Trek, really. Okay, and we're all cooperating. There's no nationalistic posturing. There's no people talking about war. And when it comes to past climate change, we wrote the book on understanding past climate. Because of our drilling since the late 60s, we were the first to develop continuous records of ice ages going back hundreds of thousands of years. Of course we have now ice cores, but we were the first ones, Gesundheit. We've attained continuous records going back for the last 100 million years, back to when the dinosaurs were running around, about climate. Constrained ocean temperature and therefore global climate. We've developed new proxies to estimate carbon dioxide levels in the atmosphere. How do you do that, right? For the last 60 million years, and that's being moved further and further back, okay, for the first time. And we've also identified some of the biggest shifts in climate change that has ever happened. For example, PETM, this is an event that happened 56 million years ago, where we had a runaway greenhouse world due to methane on the sea bottom. Being basically frozen methane, basically becoming unfrozen, being released. Methane gas happens to be about 23 times more effective as a greenhouse gas than carbon dioxide. And temperatures during Gesundheit again, during this 56 million year runaway greenhouse world, it got so warm that we sea surface temperature estimates for around New York City were in the low 90s. Okay, I don't know what it was in Boston because we don't have a record from. But you can imagine we'd probably be in the mid 80s. We never, outside of your bathwater, you don't get mid 80s around here. Okay, and then we have other ones: the greenhouse to icehouse world, the middle Miocene transition, so on and so forth. It's just, this is what the ocean drilling program has done, all through cooperation. But still, but why should we really care about collecting data from the past? Really? And the reason why is because the future is data poor. And so we have to look to the past to understand what the present, to better understand the present, because we know that there's a growing concern over the changes that are happening, basically because of greenhouse gases being put into the atmosphere. And this is going to affect the world and the society that we live in profoundly. And it's only by understanding the history of long-term climate change can we hope to understand current and try to predict the future. Because we now understand that the Earth was a lot warmer in the past. And I'm going to show you that in a couple of minutes. But it wasn't because the little lemurs were driving around in SUVs, okay? It was because of Mother Nature. And society has never seen the temperatures that we've seen in the past. So let's just do a few little things. First of all, let's talk about CO2 in the atmosphere. This is CO2 is in the y-axis. This is 1,000 years, 1000 AD. This is today here. And you can see that CO2 is a flat liner right up until the Industrial Revolution, and then we start going up. But that's just like the tip of the iceberg. Okay, this is what we're projecting right now. Okay, we're right now at about 390. We're almost at 400. And we have CO2 projections up to 1,000 if it's business as usual. And by the way, we are right now doing business as usual. Nothing has changed. If anything, predictions that we made 10 years ago, they're just as steep as the worst case scenario. On the other hand, this projections where we kind of level off at 550 is like if we get all this, if all the politicians got hit by lightning or something, well, maybe some of them, we won't mention which ones, but, and they all changed the tune, and they, we started becoming more sustainable and more green world, we can probably level it off. So what is that doing to temperature? Well, temperature has been a flatliner for the last 1,000 years. This is temperature anomaly, 0 to 1990. And you can see, if anything, maybe it got a little bit cooler during the little ice age here, and then it starts spiking up above anything that you've seen in the medieval warming. Again, this is just the tip of the iceberg, because, and this is the projections, if we get our acts together, as opposed to business as usual, we're talking about anything for about 2 degrees, maybe 4 or 4.5 degrees Celsius rise. And you may think, oh, well, after this winter, I'll take a 3 degrees Celsius warming for winter time in Boston any day. But the thing is that these temperatures are global, and they're skewed to the higher latitudes. And this is where there's a lot of problems, whether it's ice, like glaciers melting, or tundra defrosting, releasing CO2 and methane, and basically resulting in a runaway greenhouse world. Really, like 200 years. And the world has not seen, at the last time the world changed faster than what humanity is doing was about 65 million years ago. What was happening 65 million years ago? Who knows what happened?
Media.
A huge asteroid hit the Earth exactly and wiped out who? Oh yeah, I didn't hear you.
The dinosaurs.
Okay, I love it. Okay, yeah, a huge asteroid hit in the Yucatan, causing a great extinction event, including the dinosaurs. And let me tell you something, guys. It wasn't the dinosaurs' fault about this, okay? And they couldn't do anything about it. In our case, we caused the problem, we can also solve it. And so this was the last time that the atmosphere changed quicker than what we're doing today. In this case, it changed in a few years. Okay? And just to kind of finish it off, there was a survey done a couple years ago of climate scientists who published in peer-reviewed journals. Okay? And over 97% of them said, point blank, that they agree with the IPCC results, which is the Intergovernmental Panel on Climate Change, which is that the climate is warming and it's due to humanity. Okay? So in peer-reviewed journals, okay, not the Fair and Balanced Journal, Fox TV or something, but peer-reviewed journals. And so, and in fact, like an analogy, I go to the doctor, not one doctor, I go to 100 doctors, okay? And 97 of them say, look, you got a really bad illness, you got to take care of this right now. But 3 of them says, why don't we wait? Okay, and we'll wait a couple of years and see what happens. What would you do? Okay, listen to the 97 or listen to those 3. Anyway, enough of my, no more politics for now. Anyway, so let's talk about the climate record. What does the climate record tell us? Well, we're expecting a 2 to maybe 5 degree warming based on, because of the greenhouse gases. The last time we saw about less than a 1 degree Celsius change was about 6,000 years ago. And in fact, civilization has been so blessed, where the last 6,000 years or so, the temperature has changed by about 0.7 degrees Celsius. Okay? That's the most stable it's been in the last 400,000 years at least. Okay? Now, it was a little warmer back 6,000 years ago, but that was not because the people in Mesopotamia were driving around in SUVs. It was because the Earth's orbit around the sun changes a little bit from a perfect circle to a little bit more elliptical, back to a perfect circle, and the axis of the Earth goes like this, and also goes like this, every 20 and 40,000 years. And those cycles were made it so we had slightly warmer northern hemisphere summers. Fair enough. A 2 degree warming we haven't seen in about 125,000 years. And again, this is not because the cavemen were driving around in SUVs, unless you believe, that the Flintstones is a documentary. Okay? And this is again due to not CO2, but actually the changes in Earth's orbit that we predict. Actually, we can predict them back 40 million years. We can predict them into the future, going millions of years as well. And because of the warming of about 2 degrees, sea level of West Antarctica collapsed, as well as part of Greenland, and sea level was about 20 to 30 feet higher than today. The last time we saw 3 to 4 degree warming was about 3 to 5 million years ago, okay? And this is when we had little hominids running around. In this case, CO2 did probably play a role. It was over 400 parts per million back then. But the last time we saw CO2 changes that was as high as what they predict for the end of the century was 25 to 50 million years ago. And the Antarctic ice sheet was a much more dynamic ice sheet with sea level changes going up and down by 100 feet. Well, speaking about sea level changes, why should we even care about sea level changes anyway? You know, well, living in New York or Boston, maybe we should. But you know, like if you go back just 35 million years ago, there was no big ice sheet in Antarctica, and sea level was about 230 feet higher than today. And so this is not going to happen today, okay? This won't happen tomorrow. This would take thousands of years to happen, okay? If it ever happened, okay? Because the ice is just so big, it's got so much thermal inertia, we don't have to worry about that. But we don't need 230 feet. We just need 5 feet, of a 5% of that ice sheet to melt, and we'd have a catastrophe. We're talking about 5% of 230 is over 10 feet. That would be a catastrophe. You think about New Orleans, you think about Miami, Bangladesh, even along the coast along here, 10 feet. Having 10 feet, I don't know, it would be pretty close. Yeah.
Very close. Yeah.
It would be scary close, yeah, very scary close. And so, okay, so let's talk about the CO2 of the past. And so this is an ice core record going back 800,000 years. 800,000 years. This is CO2, and as you can see, CO2 never gets above 300 in the last 800,000 years. And this is direct measurements, because what they do is that they find the little ice, bubbles in the ice that has captured CO2, and they can get a direct measurement. Today it's around almost 400, it's about 390. And the last time we saw that was 3 million years ago. But if you want to go through some of the other thresholds, 450 or 500, we got to go back tens of millions of years ago. 700, 34 million years, and some of the upper ones like 900. We're talking about 40 million years ago. So society, humanity, is doing in a couple hundred years that Mother Nature could not do in tens of millions of years. And so this is CO2 here. This is millions of years ago. This is today up here. And you can see on how CO2, this is the new CO2 records, so they still need to be filled in, and they are getting filled in. But you can see this gradual decrease in their present day levels. This is sea level where it's much higher when CO2 is higher, and then it kind of levels off. And then this purple here, right in here, we start getting northern hemisphere ice sheets right in the last 3 million years. Okay, but let's zero in on this little section here, because I want to make a point. And this is what scientists have known for a long time. Okay, so here is CO2. This is millions of years ago. This is the best estimate of CO2 during that time period. The red box is what we expect for the end of the century, is what we have today. This is sea level, okay? Sea level higher, sea level lower. When sea level's higher, the ice sheet's smaller or non-existent. When sea level gets lower, that means the ice sheet has gotten bigger. And you can see that CO2 is dropping, gradually through time. But here, we'll look at sea level, very high, then boom! This nonlinear change in the climate responding to this gradual change in CO2. And so this is one of the take-home messages. A linear change in CO2, one of the forcing mechanisms for climate, can result in a nonlinear response by the climate. And we've seen this throughout time. Just 12,000 years ago, the northern part of the Atlantic Ocean, including Greenland and northern Europe, it was coming out of the deep freeze of the last glaciation, and suddenly it went back into the glacial period. And it happened within a decade. You can see this from the ice cores. And so I can give you one example after another where there's these thresholds where the climate tries to stay in the same mode, and then it becomes, the changes are so profound, there's a very, very sharp switch to another type of climate mode. And so, but my focus is on Antarctica, Antarctic climate during these time periods. And Antarctica has changed dramatically through time. And in fact, I consider it to be ground zero when it comes to past climate change because it's changed more than any other place on Earth. 50 million years ago, it was basically a temperate forest. And I'm going to show you at the end where we got some information that it was actually even warmer than what I'm saying right now. And then gradually cooled to this polar desert that we have today. In fact, it's so darn cold, temperatures would have to rise about 12 or 13 degrees Fahrenheit just to cause melting along the coastline of East Antarctica. Because it's so cold today that the ice, when it gets to the coastline, it doesn't melt. It just falls off as icebergs. It's that cold. Okay, so we went from a temperate forest to this polar desert. But how do we measure ice volume? Okay, and so let me give you a couple of little words here. You're going to see in some of my slides the word used to sea. And that just means global sea level. Okay, and on some of my figures, you'll see apparent sea level, which is just used to sea plus taking the effects of water loading on the crust. Okay, those are the only two new concepts that you probably have to see. Now, one way to get at sea level is looking at shallow marine records. You have a coastline here, sea level goes up, goes down, you pop a core in, and the sediments are going to change whether sea level's lower or higher. Same thing with the fossils. Okay? However, there's a triad of processes that control the stratigraphic record. One of them is global sea level, sure. But then there's also tectonics. Tectonics, I mean, where the shelf is subsiding due to loading of the sediments, compaction. If you put some sediments on other sediments, they'll get squeezed and subside. And then something called flexure, which means that if you put a load here, it doesn't just go like this. The whole shelf will bend downwards, like a board. Okay, so you have to basically take that into account. And then there's also sediment supply. The other one is from deep sea, and I'm going to talk about this. It's basically this, not too much chemistry because I happen to not like chemistry, but is using oxygen isotopes from little microfossils called foraminiferous. Okay, and I'm going to show you some pretty pictures of them. However, just like shallow marine stratigraphic records, it's controlled by a number of processes. First of all, ice volume from the poles. Okay, I'm going to show you how that's done. And then also temperature that the calcium carbonate is made. And then finally, evaporation precipitation effects, which is not a big deal. And then I think I took out all the slides for this new technique called magnesium calcium that has the potential to give just temperature estimates so we can back out ice volume. And then finally, of course, if you just go to Antarctica, you can get direct evidence. Ice rafting, and what is ice rafting debris? It's debris that's been ice rafted. So you have, the glacier gets to the coastline, breaks off as an iceberg, and there's usually sediments entrained inside the iceberg, inside the ice, and as the iceberg melts, it'll start dropping and dropping those sediments. Also, we can look at glacial deposits. Okay, so we have shallow marine, deep sea, and then finally direct evidence. So I'm going to talk about each one of these. So first of all, from a shallow marine section, here's the passive margin here. So it's controlled by used to sea, global sea level, sediment supply, and then subsidence. The cooling, loading subsidence, as I was mentioning before. And one of the most successful drilling projects, it was actually a series of projects, expeditions, and here's the numbers, 150. 150X is an ocean drilling program expedition that was actually on land. That's why they called it X. And so we have, these are cores, these circles here. These are cores offshore, as well as on the shelf break here, and then going into the deeper waters. These lines are seismic lines. What is seismic lines? It's using sound waves to image the sedimentary layers below the sea floor. Think of it as kind of like a sonogram of Mother Earth. Okay? And so we have sonograms, and then you can actually think of the cores as little biopsies, I guess. I don't know. That doesn't sound good. But anyway, so we have cores from the two expeditions, 150X, 174AX, as well as offshore in here. And so we used a number of we have on land drilling Okay, this is one was on Atlantic City. This is the Trump Tower behind here. So you can imagine our scientists kind of go, okay, I bet you double nothing that we're going to hit the, this boundary. Damn it, we didn't do that. Also, we can in the shallow waters we can use the jack-up rig, which is actually a ship that puts down these big pipes and can actually jack itself up and then drill in shallow waters. Very cool. And then finally, we can also, in the deeper waters, we can use the JOIDES resolution, which was on the slope in the deeper waters. So, how do we back out sea level from these shallow marine sections? Well, we use something called backstripping. It's an iterative process where we basically try to take out all the signals that's in the stratigraphic record, leaving global sea level, the global sea level signal. How do we do this? So we have an initial profile here. We'll call this A layer here. We remove that A layer. Now we can model it with computers and figure out how much the sediments would have been compacted because of this weight of the sediments. Once it's removed, we can pop it up. Then we can also pop up, we can decompact the sediments. We can flexibly remove the loading, how much the more sediment you put on the crust, the whole lithosphere will sink down. Okay, and this is an iterative process using computer programs. The result, though, is that we can basically back out. We can reconstruct the stratal geometry of the margin. So this is 27 million years back to 25.8 million years ago. You can see how we can actually back out and reconstruct the stratal geometry through time. Then the only thing we have to do after that is bring in our sediments, our sedimentary data, and our fossils to tell us what the water depth was. And so as water depth went up and down, we have to reconstruct the margins now. We can figure out global sea level. And I'm cutting it short because it's a little bit convoluted, but just I can answer more questions about it if you want. So this is a eustatic chart here from 28 million to 24 million years ago. The black is the best estimate. The error bars are shown in blue. And in this case, why do we have big error bars in some cases? Here they're big, sometimes they're small, because as you get into deeper waters, the environment becomes more stable, and so the sediments and the fossils will have bigger ranges of water depths. So this is like a deeper water, we got this estimate, this is shallower waters. And that's how we can do it for shallow water sediments. Now the other one that's really cool is stable isotopes, okay? Where we can use oxygen 16 and 18. The difference between the two is what? 2 extra neutrons. So this one's a little bit heavier, and the result is that this helps. The result is that when it evaporates, when water evaporates, say in the low latitudes, the 18s will not evaporate quite as easy as the 16s. So more 16s will become entrained into the vapor, and as it moves away from the evaporation zone, as it rains, the 18s will rain out quicker. So the clouds keep getting enriched in oxygen 16s. Okay? And as they go into higher latitudes, it's raining and then finally snowing, the 18s more easily than the 16s. So by the time you get up to the higher latitudes, the snow that falls, it's highly enriched in oxygen 16s. And that values are usually very negative, so like -20, -40 represents snow that has oxygen isotope values that are highly enriched in 16s. Now, if we have got a big glacier up here, guess what? We got a lot of 16s trapped up here in the ice. What's going to happen to the oceans? They're going to be enriched in the oxygen 18s. And that's how we can do it. And we can get this from the little shells that these one-celled creatures make, and I'm going to show you in a couple seconds. Okay? And so this basically says what I was talking about. The other thing, unfortunately, is that it's also dependent on the temperature, water temperature that the calcite was formed in. And so we do have 2 variables, only 1 equation, but we can still back out some things about ice and temperature and global climate using oxygen isotopes. And so it's not a great picture, but these are these are some of the fossils. Okay, aren't they pretty? Look at this one. Okay, ooh, right. And these are called sedimentary. These are on the order of about 1/3 to maybe 1/2 of a millimeter across. So you need a microscope. These are about the same size as well. And these live on the sea bottom. They're called benthic foraminifers. Foraminifers, that's the name of the order, and benthic because they live on the sea bottom. So what scientists have done is that they've collected oxygen isotope records from these foraminifers from different sites around the world. And the result is that we have Zakos from Santa Cruz put all the records together and made this composite record where Y is height, is age, and this is oxygen isotopes. And in a nutshell, it's kind of reversed. The higher the value, the colder the bottom waters are, and or more ice. On the other side, the lower numbers is warmer and less ice. And what you can see, here's today, and you can see we're in the coldest period of the last 60, 70 million years. If you go back and see these little dots here, these are real. This is that runaway greenhouse world I was telling you about, okay, when sea surface temperatures in the New York City area probably got into the low 90s. Yeah, that's what happened here. You can see this long cooling trend from about 55 to about 34, and then boom, this big change here. This big change represents when the first big ice sheets in Antarctica grew to continental size. For the first time, we haven't had big ice sheets this big probably in about 270 million years. And then it stays about the same, and then finally the last cooling, where we start getting northern hemisphere glaciation in the last 3 million years. So we're actually living in this short-term warm period within a 3 million year cold time period. Okay? And a couple of things I just want to point out is that values of about 2.1 per mil represent where you have anything larger than that, there's got to be some ice in Antarctica. A 3 per mil value represents where you have a fully glaciated East Antarctic ice sheet. And then finally, 3.3 is similar to what we have today. And so you can see, before about 34 million years ago, we probably didn't really, we don't have to ascribe to any large ice sheets. But once we get into about 34 million years ago, there's got to be some larger ice sheets going on in Antarctica. And so let's take a look now at what the records show us going into the past. So here's the y-axis again. This is millions of years ago. Okay. This is the CO2 record showing what CO2 was like. So CO2 was either within that range or more higher. And what these represent is sediments. Sediments preserved in the boxes, and then the little red means there was no sediments preserved because sea level dropped. Okay? When sea level dropped, maybe the ice sheet got bigger. There's other processes there. But what we did is we looked at this is from Australia, this is from New Jersey, Alabama, Northwest Europe, and you see this pretty good correlation across. There's error bars in the time here. There's really a one-to-one correspondence that suggests that indeed there were small little ice sheets in Antarctica with elevated CO2, at least as high as what we predict for this end of the century, maybe even higher. And in fact, this is a table here. Every time I show this, I don't know, maybe I shouldn't show it, but this kind of gives you just an idea of how big the ice sheet was, how big of a sea level change. This is the percent of what the East Antarctic ice sheet would be. And so we talk about an ice sheet maybe 1/3 of today's present, which would represent here, in this climate model here, to maybe 2/3, half to 2/3, which is shown up in here. And this is with elevated CO2 like this. And so in this case, we would have sea level rising well over 100 feet, maybe 150 feet. Like I said, this would not happen today, tomorrow. It would take thousands of years. This gives us an idea of what an elevated CO2 world would look like. Now, if we go into the next time period from 34 to 23 million years, CO2 now is dropping. It's getting right in that zone that we expect for the century for CO2. And what I did here is that I just put together a whole bunch of different records. Okay, so this is ice volume equivalent in terms of sea level. This is the percent of the present day Antarctic ice sheet. So 100% would represent a fully glaciated East Antarctic ice sheet. This is where it's showing the maximum, this is the minima, and this is where I'm trying to show consensus for the maxima and minimum. And here it's showing that it looks like during the maxima that that ice volume may have been larger in Antarctica than today. And you're probably thinking, wait a second. We have CO2 probably even higher than today. How can that be? How can that be? Well, this is the Antarctic ice sheet. If we removed all the ice and then isostatically adjusted the crust, because all the ice weighs down on the crust and it sinks it down. You remove the ice, it takes about 20,000 years, but it'll pop back up. So this is showing the coastline in the dark gray here of what the coastline of Antarctica would look like during if all the ice was melted and the crust popped back up again. And you can see that West Antarctica would have a big inland sea in here. The Ross Sea and the Weddell Sea would be big areas of water. And however, there's been a lot of erosion taking place and a lot of subsidence taking place over the last 34 million years. And so Wilson and Lundijk just recently came out and said, well, let's, with the corrections of basically subsidence and all the erosion, West Antarctica, look at West Antarctica now. It's all above sea level, the Weddell Sea. The Ross Sea is mainly above sea level with these long islands in here. Parts of West Antarctica, they're all above sea level. In certain places, it's actually quite high. And so it's a very different continent. And in fact, the Antarctic land area would increase by about 10 to 20%, and the ice volume would even be larger. Okay, so I don't see any problems with that. And so, in the last couple minutes before I wrap up now, let me show you the latest expedition that I was on with the Integrated Ocean Drilling Program. And this is to Antarctica, this part of the coast of Antarctica called Wilkes Land. This is with the drilling ship. And this is the coast of Antarctica here. And these are some of the sites that we drilled. And so this is actually a great picture. This is some of the sedimentologists. So he's from New Zealand, she's from Japan, he's from China, from India, and then of course the American fooling around in the back there. And so since we had to go from basically New Zealand all the way down to Antarctica, so we had to first go through the Roaring Forties, and then we had to get into the Screeching 50s. And so this is actually not my photograph in this case. So you can see the horizon, the waves breaking, and then look at this wave here. Okay, yeah. So we had 35-foot waves out there, and and of course I was on this deck here taking photographs, but I was way far back, about 50 feet. So I only saw the water rushing down the deck. But the big sign says, "Do not go out on the deck." And of course, as a New Yorker, I want to take the photograph. I'm going out. I got to see this. And I saw this. Okay. And when I saw this, I said, "Have I made a big mistake?" And but what happens is that when the ship goes into the trough, that's what you're seeing, and then the ship rises up and then crashes over the very top. So, but for that moment, that 2 second of going, "Oh my goodness gracious," Well, if I drown, my wife's going to kill me. Okay, but so since we're in Antarctica, it was beautiful. The visual. This poor penguin. He's probably looking out for killer whales. And of course, just incredible beauty out there. And so this is the stratigraphic columns. Okay, so this is millions of years ago. We got big sections going all the way back to 53 million years ago. A couple million years after the runaway greenhouse world I was telling you about. So it's super long. And they found pollen evidence. They're publishing it in Nature right now that they found tropical pollen. And not the peninsula that sticks way up north, on East Antarctica. Okay? Okay, so today it's so damn cold you would have to raise temperatures a dozen degrees just to get the ice melting, and here they have palm trees 53 million years ago. CO2 was, guess what? It was a lot higher. There's probably over 1,500 parts per million. We're not going to have any palm trees in the near future, but it just gives you an idea. And so we have, this is 1,000 meters of core, that's over 3,000 feet, drilling here, and then we got other sites and so on and so forth. Well, this doesn't come out well at all. Okay. Anyway, you can barely see it on this, and so, but this annual valves here, in the dark and light is 1 year. So we're getting about almost 2 centimeters for each year. And so instead of talking about millions and millions of years, here we're going back about 11,000 years, and it's basically like a tree ring from the bottom of the ocean off of Antarctica. Try to put those 3 nouns in one sentence. And so I'm actually working on, with some scientists from Stanford, we found the little foraminifers that I was just showing you. We're going to do stable isotope records and do other geochemical at like 5-year resolution. Never been seen before in Antarctica. Another cool thing is that after about 14 million years ago, the paradigm of Antarctic climate science, that it got so cold it became like today. And there was a study that was done just recently that suggests that the age control was pretty poor, anything from 12 to 8 million years ago, that they found that the ice sheet retreated hundreds and hundreds of kilometers inland. And that isn't supposed to happen when it's already a polar desert. And we found that this is from a core here, this is the age control, this is depth, this is age here. This little green box is where we found something really interesting, where typically the waters off of Antarctica are really corrosive because it's so cold and they got a lot of nutrients. And so the foraminifers that make calcium carbonate, they get dissolved away. And then suddenly, course 32, 33, nothing. And then we get into this beautiful, where there's lots of calcareous fossils, and which means that the water's warmed up, okay, a lot. And then after 4 cores, which is about, and each core is about 9.5 meters, boom, they all disappear again. And we think that this is that warm period that these scientists are found on the Antarctic continent. And so this is a warm period, previously undiscovered warm period that, that we can now look at in quite a lot of detail because we got oceanic records. And so in summary, this is us crossing the Antarctic Circle. And so here's some quick results because we're running out of time. And basically, we drilled over 3,000 meters. The oldest sediments were over 53 million years old, finding pollen that was semi-tropical to tropical, actually basically palm trees. And we discovered this warm interval about 11 million years ago that was previously never seen before in the record. And so, just in summary, what is next? Okay, for the young people, okay, if you're going to be going into science, whether it's in biology, whether it's in physics, whether it's geology, climate, ocean, the ocean drilling program has an expedition for you, basically. And like I said, they now take graduate students. You don't have to wait until you're a professor, an old fogey like me, doing the professor stuff. You can actually do it now. And it's just not going to be looking at old stuff. Of course, you've got to get the long course, but we're also looking at problems today. We're putting remote observatories on the sea bottom to monitor, not to look at the past, but to look at the present, for example. And we're also looking at new technology to figure, like the way we're getting CO2 records from the distant past, and looking at new links between the life sciences and the earth sciences, and then finally, a lot of expanded education and outreach. When I was on the expedition, I did video conferencing to something like 4,000 students and teachers, live broadcasts around the country and around the world, in fact. And so for the educators in the group, this is also another great place to do really, to bring the kids in contact with some really amazing science. And with that, I'll take some questions. Thank you.